You know, it's amazing when you really start to think about carbon, just how much of it is all around us.
It really is.
And I mean, it makes sense.
Yeah.
It is the fourth most abundant element by mass in the entire universe,
Yeah.
right? Like just huge.
Yeah.
And even here on Earth, it's the 15th most common element in the Earth's crust.
Yeah. And it's also the basis of all known life, right? So
Oh,
it makes
yeah.
it pretty darn important.
Right. And actually, in the human body, you know what the second most abundant element by mass is?
Is it carbon?
It is carbon.
Yeah.
Yeah.
Oh,
About
yeah.
18.5% of your mass is carbon.
I did not know that.
Right. So it's everywhere.
Yeah.
And it's in us. And today we're going on a deep dive into all things carbon. So we're going to cover its fundamental properties, all the different forms it takes, where it's found, and all of its myriad applications.
That sounds awesome. Let's do it.
So this is going to be fun. Carbon is a very versatile element. It can be found in so many different forms, from the softest material known to the hardest material known.
I know. It's crazy, right?
And it's all thanks to its unique bonding properties. So let's talk about that. Why is carbon so adaptable?
Okay, so carbon is adaptable because of the way it bonds. Each carbon atom can form 4 bonds with other atoms. So think of it like it has these 4 little arms reaching out, ready to grab onto something else. And it can bond with lots of other things, including other carbon atoms, which means that you can get these huge chains and rings of carbon atoms all linked together.
Right. So that's how you get these incredibly complex structures.
Exactly. And all of these structures, these long chains and rings, they form the backbone of what we call organic compounds and polymers. And these are stable at, normal temperatures here on Earth.
Right. That's essential for life.
Exactly.
And this ability to link up in so many different ways is what leads to those amazing allotropes of carbon that you mentioned.
Yes.
Right? It's not just one flavor of carbon, so to speak.
Right. And the way these atoms are arranged really dictate what those physical properties are and how we ultimately use it, too.
Right. And the contrasts between some of these allotropes are just mind-blowing.
Oh, they are. It's really cool.
So let's talk about some examples. We have, for example, graphite. And we all know graphite from pencils, right? It's opaque, it's black, it's incredibly soft. I mean, you can write with it. That's how it got its name, right?
Yeah, from the Greek word meaning to write.
Exactly.
Yeah.
And it's a pretty good conductor of electricity.
That's right. So with graphite, you have these layers of carbon atoms all arranged in these hexagons like a honeycomb. So you can almost picture it like sheets stacked on top of each other. But those bonds between those sheets, they're pretty weak, so they can slide past each other really easily.
That explains why it's so soft and why it can be used as a lubricant.
Exactly. It actually exhibits something called superlubricity.
What?
Yeah. So it's basically super slippery, and graphite can actually act as a thermal insulator, too.
Interesting. So graphite is a great conductor of electricity, but it can also be a thermal insulator.
It can be both, depending on the form it takes.
Wow, that's fascinating. And under normal conditions, graphite is the most stable form of carbon.
Yeah, it is. It likes to hang out in those layers.
Okay. So now let's talk about diamond, which is sort of like the other end of the spectrum. It's the opposite of graphite in many ways. Diamond is transparent. It's the hardest naturally occurring material that we know of. And it's a fantastic electrical insulator. So how do we get such different properties from the same element?
So with diamond, instead of these flat layers, the carbon atoms are all bonded together in this really strong 3-dimensional lattice. So each carbon atom is connected to 4 other carbon atoms in this really tight network.
So that explains why diamond is so hard.
Yeah, those bonds are really difficult to break. That's what makes it the ultimate abrasive.
Right. And the best known natural thermal conductor, too.
Yeah, it's pretty amazing. It's almost the best, yeah. So you've got these 2 materials, graphite and diamond, both made of carbon. But the way those atoms are arranged makes a huge difference in their properties. One is super soft, the other is super hard. One conducts electricity, the other one doesn't. One is opaque, the other one is transparent. It's really wild.
That's incredible. So it's all about the atomic arrangement. And these aren't the only ways that carbon can exist, right?
Not at all. There are so many other forms of carbon, each with its own unique properties.
So like what?
Okay, well, there's carbon nanotubes, for example. They're these tiny tubes of carbon atoms, and they have some of the highest thermal conductivities of any known material.
Really?
Yeah, and they're also among the most anisotropic materials known.
Anisotropic. That sounds complicated.
It's not that complicated. Think of it like wood. It's much easier to split wood along the grain than it is across the grain, right? Well, anisotropy is kind of like that, but on a molecular level. It means that the properties of a material can be different depending on the direction you're looking at it. So carbon nanotubes, for example, they conduct heat really well in one direction, but not so well in other directions.
Interesting. So it's like they have a preferred direction for heat flow.
Exactly. And then there's graphene, which is like a single layer of carbon atoms. So it's basically like one of those sheets from graphite, but all by itself. And that has some pretty remarkable properties, too. It's super strong, super thin, and it also has incredibly high thermal conductivity.
Graphene, yeah, I've heard of that. It's
Yeah.
supposed to be like a wonder material, right?
Yeah, it has a lot of potential applications.
So we've got nanotubes and graphene. What else?
Well, there's also amorphous carbon, which is basically carbon that doesn't have a regular crystal structure. So it's kind of like a jumbled mess of carbon atoms. And you find an amorphous carbon in things like charcoal, soot, and activated carbon.
So it's not as organized as diamond or graphite.
Right. And because it doesn't have that organized structure, its properties are the same in all directions.
Okay. Makes sense.
Any
Any other interesting forms of carbon?
Oh, yeah, lots more. There are fullerenes, which are these molecules made up of carbon atoms arranged in these hollow spheres. And one of the most famous fullerenes is Buckminster fullerene, or C60, which looks like a soccer ball.
C60, that rings a bell. I think I saw a model of that in the science museum once.
Yeah, it's pretty cool.
So we've got these spherical carbon molecules. Are there any other shapes?
There's Lonsdaleite, which is a hexagonal form of diamond. It's actually even harder than regular diamond.
Hexagonal diamond. Wow.
And then there's carbon nanofoam, which is a really weird one. It's a pure carbon material that's actually magnetic.
A carbon magnet. That's crazy. I didn't even know carbon could be magnetic.
Yeah, it's pretty wild. And there's Q carbon, which is another interesting form of carbon that can be used to make diamond at room temperature.
Room temperature diamonds. That sounds like something out of science fiction.
It's pretty cool, right? And then there's carbene, which is made up of these long, straight chains of carbon atoms. And glassy carbon, which has a structure that's kind of related to fullerenes.
So carbon can take on all these incredible forms. It's amazing. And where do we actually find all this carbon? I mean, I don't just see diamonds and nanotubes lying around everywhere.
Well, carbon is all over the place, but it's often hidden away in different reservoirs. So, for example, in the solid Earth, there's an estimated 730 parts per million of carbon. Now, that might not sound like a lot, but when you consider the size of the Earth, that's a huge amount of carbon. It adds up to something like 4,360 million gigatons.
4,360 million gigatons.
Yeah. It's hard to even wrap my head around, and that's just in the solid Earth.
Right. And then you've got the atmosphere, which contains about 900 gigatons of carbon, mostly in the form of carbon dioxide.
Right.
And the oceans contain even more carbon, about 36,000 gigatons, which is dissolved in the water.
Wow, that's a lot of carbon. And then there's the biosphere, which is all the living things on Earth. And that contains an estimated 550 gigatons of carbon, although there's still some uncertainty about how much carbon is locked away in deep subsurface bacteria.
So carbon is in the air we breathe, the water we drink, and all living things. And then, of course, there are the fossil fuels, which are essentially concentrated forms of carbon.
Yeah, exactly. And those fossil fuels, things like coal, petroleum, and natural gas, they represent significant carbon reservoirs.
Right. How much carbon are we talking about?
Well, coal reserves are estimated at around 900 gigatons, with potentially 18,000 gigatons of total resources. And oil reserves are in the ballpark of 150 gigatons.
Wow, that's a lot of fuel.
Yeah, it is. And then there's natural gas, which is mostly methane. Proven natural gas sources contain about 105 gigatons of carbon, but there are estimates that there could be another 540 gigatons of carbon in unconventional natural gas deposits, like shale gas.
And what about methane hydrates? Those are those icy deposits of methane that are found under the sea and in polar regions, right?
That's right. And they could be a significant source of carbon as well. Estimates vary, but some sources suggest that methane hydrates could hold anywhere from 500 to 3,000 gigatons of carbon.
That's a huge range.
Yeah, it is. We're still learning a lot about methane hydrates.
So we've talked about where we find carbon on Earth, but I also remember reading something about carbon-rich asteroids.
Yeah, that's right. In the outer asteroid belt, there are quite a few asteroids that are rich in carbon. And while we haven't actually sampled any of these asteroids directly, they represent another potential source of carbon in our solar system.
So we could potentially mine carbon from asteroids in the future.
It's possible. It's definitely a long way off, but it's something that people are thinking about.
It's amazing to think about all the places where we find carbon, from the depths of the Earth to the vastness of space. So we've explored where carbon is found and the different forms it takes. But now I want to talk about how we actually use carbon. I mean, obviously it's essential for life, but what are some of its other applications?
Well, beyond its role in living organisms, carbon is also incredibly important for a wide range of industrial applications. And a lot of these applications depend on those unique properties of the different forms of carbon that we talked about earlier.
So let's start with the most obvious one, fossil fuels.
Right. So fossil fuels like coal, petroleum, and natural gas, they're basically our primary source of energy. We burn them to generate electricity, power our cars, heat our homes, and so on.
And these fossil fuels are essentially just concentrated forms of carbon that have been buried underground for millions of years.
Exactly. And when we burn them, we release that carbon back into the atmosphere as carbon dioxide.
Which is a major contributor to climate change.
Yeah, it is. So there's a lot of interest in finding alternative sources of energy that don't rely on fossil fuels.
Absolutely. So moving on from fossil fuels, what are some other ways that we use carbon?
Well, carbon is also a key component of a lot of materials that we use every day. So, for example, cellulose, which is a natural polymer found in plants, it's used to make paper, clothing, and even building materials.
Right, and cellulose is basically just a chain of glucose molecules, which are made up of carbon, hydrogen, and oxygen.
Exactly. And then there are animal-based materials like wool, cashmere, and silk, which are also made up of carbon-containing polymers.
And then there were all the synthetic materials that we use.
Right. Plastics, for example, are synthetic polymers that are often made from petroleum products.
So plastics are also based on carbon.
Yeah, pretty much.
And what about carbon fiber? I know that's a really strong and lightweight material that's used in a lot of high-tech applications.
That's right. Carbon fiber is made by heating filaments of organic polymers, like polyacrylonitrile, to really high temperatures. And this process creates these really strong, thin fibers that are mostly carbon.
And carbon fiber is used in everything from airplanes and cars to bicycles and tennis rackets.
Yeah, it's a really versatile material.
So we've talked about cellulose, plastics, and carbon fiber. What about diamond?
Well, diamond is obviously a very valuable gemstone, but it also has a lot of industrial applications. Its hardness makes it ideal for cutting, drilling, grinding, and polishing. And it's also used in some high-tech applications, like in diamond anvil cells, which are used to create extremely high pressures for experiments.
So diamond is not just pretty, it's also very useful.
Exactly. And with advancements in synthetic diamond production, we're seeing even more potential applications for diamond in the future.
Like what?
Well, for example, diamond could be used as a semiconductor in microchips or as a heat sink in electronics.
So diamond could be the key to faster, more efficient electronics.
It's possible.
What about graphite? Does that have any industrial application?
Oh, yeah, definitely. Graphite is used in a lot of different things like batteries, lubricants, and even nuclear reactors. And of course, it's also used to make pencil leads.
So the same element that could be used to cut through steel can also be used to write on paper.
It's pretty amazing, isn't it?
It really is. And what about those organometallic compounds that you mentioned earlier?
Oh, yeah. So organometallic compounds are basically compounds that contain a bond between a carbon atom and a metal atom. And they're used in a lot of different chemical reactions and industrial processes. For example, they're used as catalysts, which are substances that speed up chemical reactions. And they're also used in the production of plastics and pharmaceuticals.
So carbon is even involved in making the medicines that we take.
Exactly.
It's amazing to think about how versatile carbon is.
Mm.
It really is a fundamental building block of our world. And it's incredible to see how its unique bonding properties lead to such a wide range of materials and applications.
Yeah, carbon is pretty special. It makes you wonder what other secrets it might be hiding.
It does.
Yeah.
So there you have it. That's our deep dive into the fascinating world of carbon. From the stars to our own bodies, this element is truly everywhere, shaping our world in countless ways.
And we're still learning new things about it all the time.
That's right. So thank you for joining us on this journey.
And thank you for listening.